Hello, my name is Ishan Kapse. I'm currently pursuing my master's at CSU. Today I will shed some light on the STT RAM technology, its limitations, and some of the currently proposed techniques that make STT RAM a better alternative for the future. Let's start with understanding the need for a new memory technology. As we all know today, there is a race to put in more and more processors on chip to improve the processing power of devices. Not just the hardware, but even the software is being developed in such a way that it is optimized to use as many cores as possible. Increasing level of computation powers combined with fine-grained parallelism shoots up the resource utilization per core in today's multi-core systems. But we can see that technology advancements in memory cannot keep up with its processor counterpart. This creates a memory wall. Since technologies such as SRAM, DRAM, or the hard disk are nearing their saturation, it is important to look for alternative non-volatile memory technologies. Why non-volatile memory technologies instead of volatile memory counterparts? As requirement of processing power increases more and more, the dynamic power consumption in a memory system increases drastically. Hence we choose non-volatile memory over volatile memories because they have low dynamic power characteristics since there is no refresh required in these memories. Some of the other benefits include low leakage current, higher density, and high write cycle endurance. Three main technologies are being worked upon right now: the PCM, the MRAM, and the STT-MRAM. PCM has a better density than SRAM but has a low write cycle endurance, almost 10 to the power 8 cycles. STT-RAM on the other hand has a high write cycle endurance, almost 10 to the power 16 cycles. It exhibits a lower leakage energy than SRAM and has comparable read latency. MRAM and STT-RAM showed similar device characteristics, but MRAM has a more complex structure, is costlier to implement, and has poor scalability beyond 65 nanometer. Now let us look at the structure of a basic STT-RAM cell. On the right we can see a basic STT-RAM cell. The red line represents the drive line and the blue line represents the sense line. The isolation transistor or the access transistor is used to read or write data into the STT-RAM. The portion between the drive line and the sense line is called as the magnetic tunnel junction. It consists of two ferromagnetic layers called as the free layer and the fixed layer or the reference layer. Between these layers we have the tunnel barrier, which is a thin insulating non-magnetic layer. To understand STT, we first need to understand the TMR effect. Now, the TMR effect states that when two layers share the same magnetic orientation, then majority electrons tunnel through the barrier, thus giving a high conductance and a low resistance. This is depicted by a logic 0 when storing data. Conversely, when the two layers are not magnetically aligned, then only a small portion of electrons tunnel through, thus giving a low conductance and a high resistance. This is depicted by logic 1 when storing data. To read a cell, we need to apply a small voltage between the sense and the bit lines. The amount of current flow is sensed, and if it is low, it is represented by logic 1, and if it is high, it is represented by logic 0. To write, a high current is passed through the MTJ to change the magnetic orientation of the free layer. For this purpose, we need large write amplifiers. Some of the advantages of this technology is that it is non-volatile, it has high density, high capacity, high endurance, it consumes low leakage power, and it has low energy consumption during read cycles. The read or write latencies are comparable to that of the SRAM, and it shows high scalability since write current varies inversely as the technology node being used. Now we come to the crux of this discussion, and that is the limitation as of now. The first challenge is that during switching from parallel to anti-parallel or anti-parallel to parallel, we sometimes encounter random thermal kicks acting on the magnetization of the free layer. These kicks are non-deterministic and can cause switching of the free layer. This compromises the thermal stability of the MTJ. The second challenge, as mentioned earlier, is the requirement of the high write energy. The third challenge to this technology is the high write latency of the STT-RAM, which is much higher than that of the SRAM and the DRAM. The fourth challenge has been recently identified, and that is the increasing number of read disturbances with reduction in the technology node. This is basically because the margin between the write current and the read current is decreasing with decreasing technology nodes. Some of the proposed solutions to overcome limitations are given as follows. Smullen proposed generating a thermal noise model using the HSPICE and LHG differential equations to accurately predict aberrations in the MTJ during switching. Now, by predicting these aberrations, one can improve their design in such a way that it is more thermally stable during switching. To reduce the write current of the MTJ, we need to reduce the large intrinsic current density required for the write operation. This can be done in two ways. Inducing perpendicular anisotropy in the in-plane layer can cancel the demagnetization field in the in-plane MTJs and thus can reduce the large intrinsic current density required for write operation. The advantage of this is it does not require in situ heating during deposition and thus integrates better with CMOS processes. Now different memory subsystems such as the cache, the DRAM or the storage require different retention times, and by profiling these retention times across various memory subsystems and designing different memory MTJ structures, we can optimize the model. We can also optimize the model using an algorithm such as an invert coding. Kandemir suggests the use of a selective write-back policy while using the STT as a DRAM alternative. In this case, a selective write-back policy is performed, in which case the row buffer is not written back to the array if it is clean. It is only written back if it is dirty. Kandemir found by simulations that almost 60% of his data was clean and thus eliminated a lot of write-back energy and reduced access latency of the clean row buffers. Henry Park suggests the use of multiple MTJ memory elements per cell. This technique shows modest improvements in cell density and write current efficiency of a cell per MTJ. Another work by Smullen suggests the relaxation of non-volatility of an STT-RAM cell, specifically to reduce its retention time by reduction in the planar area of the FL. Shafai suggests the use of FinFET-based access transistors. Now these transistors, in comparison to MOS-based transistors, show a small improvement in read and write latencies. Zhang proposed a custom-designed X mode that uses differential sensing in the sense amplifiers. Such a configuration minimizes the read disturbance error. Now we will look at some of the applications of the STT-RAM technology. STT-RAM is used as a hybrid cache system which uses an advanced adaptive block placement and migration policy. Now this block placement uses an access pattern predictor to identify if a certain block of data can incur a certain write latency. If it can, it places the block in STT-RAM, otherwise places it in the SRAM. Another application is the NV sleep proposed by Xiang and Radu. It uses an STT-RAM to implement rapid shutdown of cores without loss of execution state. If in NV sleep implementation, all memory-based functional units that are not write latency sensitive are implemented using STT-RAM, while others are implemented using SRAM. Data of SRAM is stored in STT-RAM. When power is restored, content of SRAM is got back from the STT-RAM. Cores can thus be turned off frequently and even for short periods of time to save power. Loop-aware sleepy instruction schemes is another application of STT-RAM, which uses STT-RAM as an instruction cache and the SRAM as a loop cache. Basically, for small loops, the SRAM calculates everything in the loop, whereas the STT-RAM is free to calculate the bigger things. Several different algorithms proposed by many engineers that work on either improving performance or reducing the energy consumed. Future prospects are that spintronics is a growing field right now, and it promises delivering instant on high-speed portable devices with a great battery life. STT RAM can also be used as a universal memory. Worldwide corporations like IBM, Intel, Samsung are looking into this and investing in resources for research in this field. Excellent scalability combined with great packaging density appeals very well to the current trend of fitting more and more into a system. In, con- in conclusion, I would say that STT-RAM shows tremendous promise for being used as a universal memory for both low-power embedded systems and standalone applications. Four basic challenges of the STT-RAM need to be addressed, and we have several approaches to do so. Lastly, I would say no system is perfect, and it all comes down to making calculated trade-offs between several parameters of the system as per the application, and this is what needs to be done in the STT RAM. Thank you.